So, yeah, there was, I guess, little time to do this, so we ended up. Anyway, so.
Yeah, give me like 10 minutes, and then I'll come back up and we'll do
Yeah.
the interaction with the
Okay.
bottom. Yeah.
All right. So let's talk about how many people are using Azure. Okay, 1, 2, 3. How do you like it? Nice. So.
I'm starting to work with that.
Yeah, you're starting to work with that.
I
Okay.
just started working with it too, so I'm still getting used to it.
Yeah. Okay. Well, let's see if we can put it together with Azure. All right. So I'm gonna put this on and.
Clip to the, no, I think there's a, trying to take the clip off
Yeah.
at the top. Hmm.
Some. Can everybody hear me?
Yes, sir.
Okay. All right. So what we did. What we did here is we went into Azure and we took a model that is readily available. And I need my mouse. All right. So there are some built models already in Azure, right? Okay, so it's copying, showing here. All right. So let's do this. Okay. So this was the simple model, create our simple model. I guess what you will see in Azure that there are these navigational icons here, and there are pre-made components, and some of these components you can build into projects. So for example, in this project. So this is the project that I started working on and tried to integrate or take code that I ran in R, and then I added it here. So let's take a look here at this model. Okay, is that, I guess, center? So now, can everybody see that really clear? Maybe enlarge it a little bit? Okay. All right, so let's walk through this first. I added this so I could just leave it alone for now, basically, and I added this here, this component here. Basically, the original model basically took the breast cancer data set, and in the breast cancer data set, it's all numeric. So now, if we were to take a look at this data set and just, okay, so it looks like I need to log in again. I guess that's the nice thing about Microsoft, they kick you out fairly often, so you have to log in. Let's not say anything bad about Microsoft, right? I mean, they paid for, yeah, they paid for the room here, so you know, it's nice of them. We were supposed to have actually somebody from Microsoft, but the schedule just couldn't be made. But next time we're going to have somebody, an expert from Microsoft, and he's going to basically even complete this part. So, okay, so basically we grab this breast cancer data set, and if we visualize that data set, basically, you see that it's all numeric, and class, this column here, class, is the one that we're going to predict, but we're going to use this data set to train the model and then predict. Now here is basically the whole process, if I may explain it. So if you have a data set, you know, just grabbing any data set is not going to basically be meaningful unless there are some decisions made in it. In other words, if you want to build a model for breast cancer, to predict breast cancer, a doctor or somebody has to say, this patient has cancer, this other patient doesn't have cancer, or this patient has high risk of cancer, that patient has low risk of cancer. So somebody has to score it in the first place. Now let me give you something else that is kind of simple to follow, but difficult to apply. So let's take an example. If you have the best diagnostician in cancer, building a model is like taking this man's brain, which is usually impressive, and codifying that in the machine. Okay. How do we codify that? It is through that data set that he, as the expert, applied his best expertise and knowledge. Now, it could be also a statement of fact that actually these people did have cancer, and they did experience the cancer, and those that didn't, they actually didn't. Or it could be an expert applying that. Either way, what you're doing is that you're taking real facts or best expert, best expert opinion, and you're using that to train the machine. So to train this this model, we have to use that, and by identifying also to the machine which one are we going to predict and which one we want to use to predict. So for that, the predictors, we call them features, and the outcome, or the predicted column, is the outcome. So now you have features and outcome. Now, the other thing that is also equally important in applying that is that what are we trying to predict? So in this case, it's a binary outcome, right? So that makes it really simple. That means applying, for example, let's say linear regression is useless because linear regression is a continuous outcome. In this case, it's really binary, up or down, 0 or 1, yes, no. positive, negative. This is what we call binary outcome, and that means there is nothing in the middle. Now, having said that, it doesn't mean we can't assign a probability to that prediction, which could be useful. Okay, so now, one of the things that I also added into this model. Now, remember, this is a model that is built for training. So now we've seen what the data looks like, and I wanted to add something here. It's called PCA, Principal Component Analysis. What's intended in this generally, when you have wide data. Now let's back up a little. In applying predictive modeling, you have to think of the data set as a single spreadsheet. You have columns and you have rows. And the columns are what we call the features or the predictors or the outcome for that matter. And then the rows are observations of patients. So each patient is represented by one row. That's an observation, a case, a temperature measurement, a something. Okay, so it's an observation, and all the observations have basically data from that particular observation. Now, the other thing sometimes is that where you have wide data, what you want to do is that you want to reduce that dimensionality reduction. Okay, in data science, also known as dimensionality reduction. The purpose is to take that massive wide data and reduce it, maybe, and then with the PCA, what it produces a smaller number of columns. But it doesn't, it may not necessarily pick column A or column B. It could be that it, what it does, it figures out or it eliminates the possibility of column A and column B having any correlation between them. So in order to avoid that, it generates a third column completely different, but it reflects the value towards that contribution, towards that prediction. So with the PCA, with the use of the PCA, remember we had, how many columns we had in that? I think it was 11, right? So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we had 10. Now, what we got, naturally the class is preserved. And to preserve the class, that means all the others, that means 9 would be reduced. So now the reduction, if you take a look, class is preserved because you don't want to fool around with that column. That's the one you're trying to preserve and predict as accurately as possible. And out of that, we were able to select 4. Now in the PCA, you can actually select how many you want. Now that may be beneficial or it may be detrimental to your model. So what you could do is that you try this and that. Now notice something. A lot of the columns that we were looking at, they had, if you look at their histogram, some of them were all over the place. What you find with the PCA that they, some of them in fact may begin to take that normal distribution shape or bell curve. And that's why, for example, column 3 has that kind of bell curve. Now, not not exactly, but it's pretty close. And, yeah,
This reduction, you reduced the 6 columns to 4 columns. Did it do this for you, or did you decide which one you were submitting? When you went from 10 columns to down to 4,
yeah.
how did that happen?
This is what's called the PCA. That's an algorithm that is built in R or in the Azure ML or in Python. You can actually apply it in R just the same way. Now, of course, the format is different because usually in R it's just a one line. Okay. As opposed to here, it is a module which is made easier to be, I guess, user-friendly. So if we look at that PCA itself, you can see that it gives you some variables from which, but here it shows you that selected columns, the selected columns that we choose to use as an input into the PCA. But if you click on this, the launcher, you can actually pick and choose which of those columns you want to include in that reduction. Right? So in this case, what I'm showing you is that with the exception of class, I've used all the other columns because I wanted class to stay out, not to be confused, right? Because that's the outcome. Does that explains a little bit?
I was explaining.
Yeah.
It's very similar to something you've written that in like and on, so I'm very familiar.
Yeah. So these are algorithms that are built, and that's the beauty of scientific computing in languages like R and Python scientific computing, not the Python application or application building. Okay. And by having these algorithms readily available, yeah, you don't have to know how they work, but also it carries a danger, because if you misuse it or use it at the wrong place, or you could basically be causing harm to your results. You could actually be degrading your results. Yes?
Is it an algorithm, or is it more like a neural network that kind of learns?
It's an algorithm.
So it's an algorithm?
Yeah. Yeah.
So how do you check on the validity of your model? How do you know if it's going to be
Well,
presenting what you
you always, in data science, you always take something like that as a research project. So you try this, you try that, and you compare. You try 2, 3, 10 different things, and you compare results. Okay?
In Azure, where are my options to tweak that PCA algorithm? Because just looking at it, sometimes I feel like that might be too liberal of an approach with that cleaning. I mean, for an example, it's great.
Yeah.
But for a general data set, you really want to dig in there and make sure you're not making a mistake. So
Yeah.
how would I tweak this?
Well, I can't answer for a lot of the modules in a lot of these modules in Azure are a little inflexible. They are made, I guess, you know that simplicity compromises flexibility, right? So flexibility at one end and simplicity at the other end, and basically there is a sliding scale, right? So basically then what some of these you can play with, and some of them are fixed. In fact, if you try and modify, you'll get errors. But in this case, this is where you change, basically, this is where you change the column. So I could take, for example, monopause and throw it out. and it would, now, I would still get 4 because I chose 4 columns, okay? But naturally, then any value that is added by monopause would definitely have an impact in terms of gender, right? Now, if the value, if gender and monopause, as an example, if they were correlated, then it's possible that taking out monopause may not cause that much of a difference in the outcome, right? So, but these are the choices that you have to make, and it really is an experiment. So you try this and try that and try that. Naturally, if you, and now what I wanted to emphasize here also, I'm using the free version of the Azure ML, which all of you can do that without having to pay for it. So these models do exist, and you can go and look at them and play around with them. Okay? Make sense? Yeah. So anyway, so let's put this, the monopause back in where it was. Now, I initially added this particular module, the PCA module. I added it in on purpose. Now, the other thing I want to show you, that this is where the number of columns that I set, I wanted, where I could change. So it goes to your question. There are some flexibilities which you can do, but there are naturally limitations. It's a good tool to kind of learn if you're not sure what you're doing, but also it can be frustrating as well. Okay? So going back to where we were, so when we made changes to this, it's best that we rerun it. Okay? So now, when you run the model, you can actually choose to run one, and anything that was before it, that was reset for any reason, it will rerun again. So if I choose to run the selected, what will happen is that the breast cancer data, it's not that complex, it's just a simple loading of the data. But nonetheless, it will rerun again if it was reset. So here is what happened. And now we run it and we have the results, and we're back to, see, you see that sign here? The green sign, check. That means this was run and it's ready to show you the results. But if it isn't, you can check the results, but chances are you're not going to see anything. Okay? So we're good? Awesome. Now, the other thing in training is that you want to split the data as well. And the reason you split the data is that you train on a set, and then you use the prediction, the model that you ran, use that to predict. So, also this is one of those modules, you have a little bit of flexibility to select how you want to split the data. So if we click on this, now we're not going to go into all the details there, but basically this is the split, 0.75. Usually that's assumed to be, or defaults to, 0.75 is the training module, or the training set. The training set represents 75% of that data set, and the test set is 25%. Okay? Now, So we split the data set, and then basically what you have is in exit 1 or output 1 is the training data set, and the second is the test set. So let's look at what R module we're using. Now in the R module, this is one of those modules that are pre-built by Microsoft to execute R script. So if we were to look at that and analyze what we're looking at. Now this is the training set. In the training set, we're calling library E1071. This is a well-known library, very rich with algorithms, and it's also very easy to use, and it has been around for some time. Okay, so now basically the way we split is that we choose the features from the data set, and then we choose the labels. And then we create the training data from the features and labels. And then we run the model. Now when we run the model, basically what we're using is naive Bayes. Now the naive Bayes is a well-known algorithm, naive Bayes classifier. So classifies or binary classifier. Now, if you remember, class was the predicted or the outcome, right? And then the rest of the training data set, everything else. This usually is what's used to separate the predictor from all the rest. Now, we didn't specify any particular column, but the dot represents all of them. When you put in a dot there, basically what you're saying, use all of them, but you can. And that's a whole different session, actually, we do in our boot camp about these, to explain how to do that, because you can also not just pick. Yeah.
What's the definition of class? What do you mean by class? I know it's called or something.
Yeah, class is the column, the outcome column is called class. Not the, it's not a programming in the programming or Java, especially Java, class and inheritance and all that. This is, yeah, some of the algorithms sometimes require the predictor or the predicted to have a particular label, a particular name, such as label. That's common a lot, or in some cases the word class. It makes it easy, I guess, to, these are, at the end, these algorithms are programs, and they need to follow, I guess, whatever was built and designed in them. Yeah?
So you're saying that the class identifier is actually that using R, but it's using Azure, so Azure knows what it's looking for in R?
This is actually an actual script that you can take and run in R. This is an actual R script, and the integration. See, this is what's powerful about R. It's not just it's recognized at being powerful and vast, but also that integration. A lot of companies. Last week I found out SAS is integrating R. I mean, this is huge, right? This is massive. This is earthquake. Yeah, this is the mountain coming to Muhammad. Right? So, so the integration allows you to, and this is one of the beauties of R. It has facilities that you can actually run something called RServe. It runs in the background. And all the libraries that you have on that server or on that machine, you would be able to call RServe and run these scripts that are R script, fundamentally R script. And they are actually pushed out to the R server, and any time that you run one of these scripts, it creates an R session on its own, independent of everything else that could be running at the same time. So in other words, it's like creates an environment, and that's really also significant in R understanding environments. It's like encapsulates that whole exercise, the libraries that you load. And that's why, for example, you see that we're calling that library E1071. There are 12,000 libraries in R. Now, this was probably 3-4 months ago, maybe 13 by now. The contributors into R are like awesome skill set and domains that almost in every science, in every domain, econometrics, financial, neurolinguistic, anyway. But the point I want to make in this is basically similar. So what they have is that they have an R environment to which these scripts are pushed to, just like calling an API, and then they come back with the results. So this is basically what that did. Yeah.
The thing is that we have called that the library is in Azure, it's actually going up to another environment where that library exists, running the script and it's giving you back results? Or is it?
Yes, it gives you back the results.
So,
In which environment? In your existing environment?
In the calling environment.
so it doesn't, so what you're saying is that when you make an R code in Azure, you don't actually need any special identifiers to tell it, oh, I'm using R code. It just automatically.
Well,
does
this
it.
particular one was pre-built, but the one I said, we'll look at it later. I was actually running all sorts of codes in there, R codes that I tested. Now, one of the problems there, you see that X there. I think something went wrong with the connection. Something. I may have to get out and go back in. Yeah. So to go back to your point is that you can actually do these things. Yeah, so what happened in, well, let's hope it all comes back on, and we may be all good to go. Looks like we're back on. Yeah, something went wrong with the video driver. I guess probably some sort of a conflict between the two, because it's an image of.
Maybe I have one question here.
gonna say in Azure, there is a list that our libraries that they already have, or they want to use in our library, that they don't already have. You have to put it in and unpack it and do what is around that.
Yeah, yeah, that's good. Yes, because not a lot of libraries are loaded in that environment, and I guess, you know, it's still in more ways than one. A lot of these integrations with R are experimental. Not, you know, this isn't about Microsoft. A lot of these have not been properly tested. What I mean by that, when somebody writes a library, builds a library for R, if they put it out to CRAN, C-R-A-N, which is the project for R, that foundation, it gets tested. It gets tested and validated, and it needs to meet certain standards, and for that, basically, you know, it's validated by many scientists. So if somebody builds an algorithm about some new theory that somebody came out with, it gets really vetted. Okay. But a lot of these integrations, for example, of R, they are not put to the same rigor and test that R and the R Foundation are putting in. Okay, so it's still, even as, I mean, it's great because it makes it easy for somebody to put together something like this, but at the same time, you know, whether it works exactly the way it was intended or not, it may or may not be. And that goes to your point. See, I tried to find some of the libraries to produce an ROC. The ROCR library, for example, is not there. Because I wanted to show a quick comparison. One of the outcomes down here in executing Python is that it produces an ROC, but the code in there is really long, and I wanted to show you a comparison of how much less coding you can do in R to produce the same results, except I found out, RORC is not there. Anyway, so to go back to this, the way it's mapped, it will show inputs and outputs. And in here, this is like, what's the input? It's a data set. So the name data set, wherever it is used, it's taken to mean the input that was brought in, or it was taken in from somewhere. And then the model is the output. What comes out is the model. Okay. So where you see model here that receives that naive Bayes application of that algorithm, using the class being the outcome or the predicted, and everything else from that training data, everything else is used to predict. So then the model is coming out of there, and if we look at it here, this is the trained model. Except in this particular situation, they put it into a learner.net, some .NET code, or I suppose this whole component is built actually in a .NET, like a .NET component, and it pushes the R code to the R serve, and it receives it back, and what it receives back is basically then put out as an output. The other thing is that, so we split the data, we take the data set one, which is the training, and we run it through that training model, okay, which we're looking at here. And then when we look at the scoring model, which runs the this is the scoring model. So the scoring model takes the trained model and runs it against the test data. In other words, it's not training on anything now, it's predicting. So it takes the training data and the test data, and it runs on that, and what comes out naturally is scores. And what the scores are, if we were to look at them, now we're going to run this so at least it refreshes, and then we'll look at it in a minute. Meanwhile, we'll take any questions you have. Okay? So we're going to let it run, and then we will see what comes out, the scores, what the scores look like. And then they are taken from there and they are put into that Python script to produce an ROC for that. How many people know what ROC is? Yeah. Basically, this is a representation of the cumulative effect of the scores. In other words, if you were to think of false predictions and true predictions, this is basically the mapping of true predictions, and the X is the false predictions. What it reflects, if you were to think of flipping a coin, right? So flipping a coin is a 50-50 probability. Small numbers, you may see some deviance, but in large numbers, you then basically see it's going to go back to what we call central limit theorem, right? The law of large numbers. Okay. So basically, a representation of the true positives and true negatives, true positives and false positives, in other words, the head or tail, is going to be actually a line, a diagonal line in that Y on X, right? But that also demonstrates the value or the effectiveness of a model. So if your model is a little bit above that diagonal, or sometimes could be even worse, okay? Then basically what it's telling you, it's not really valuable. Or when you're comparing 2 or 3 or 4 or 5 and more, you can actually see these lines separate, and you'll be able to judge for yourself which one. However, that also could be equally misleading because, okay, it looks like it's still running. Okay, let me take this out so it doesn't disrupt. And run it again. Yeah, so this is, now the ROC is just one measure. In other words, it's effective in certain given situations. Other statistical ratios are more meaningful in different situations. But in this case, I guess the designer of this module chose to the ROC. It's a good way of in this given situation, but it shouldn't be the only one that you measure your performance. or the performance of your model. Okay, so it looks like we're getting there, so let's look at what the scores were. So if we visualize now what came out of that scoring model, now, you see, we have naturally the class, which was always there, and it's not taken into consideration in the prediction. It's eliminated, because the model would look only for column 1, column 2, column 3, and column 4. And then the prediction is in the classes, so you can see, for example, in class here and classes, it's a 1. But then also, it's not always accurate. And if we go down to this one, you will see, for example, here, this is A0, but here, this is A1. Okay. Now, the other thing that comes out of that model is the probability. In other words, the probability usually determines, and there are ways to set thresholds and so on, but we won't get into that today, definitely. But you can see, for example, that it's really, the classes are really a reflection of the probability. You would rarely have, I mean, look at that, even is a 480048, I mean, really low probability. Now, let's see if we can find one that is close to the 50%. I doubt if we're going to have anything close, but yeah, 0.6%. Here's one. Yeah. Okay, so 52. Okay, that's usually how the decision is made. Okay. So, questions? We're good? Awesome. Now, let's then take a look at that ROC, that the Python.
That's what I was gonna ask, is the ROC.
Yeah. Yeah, so in R you can do it much more efficiently, and I think we're beginning to. You're ready?
I am ready.
I think I've taken more than 10 minutes, right? Yeah. Okay, so let's take a look at that ROC. Naturally, this is the resulting data set that came out, so it's available here. But then also, this is the ROC. So basically, instead of that diagonal line that goes from 0, 0 to 1, 1, this shows that lift, that added value in the prediction. Sometimes you use accuracy. This is a combination of sensitivity and sensibility, right? Something like that. Yeah. So this is basically, this shows you your model. Now here's the thing. Let's run a quick rerun of this. Let's remove that PCA. And take a look if that would change much. Now next time, we'll do much more than this, but for this time, okay, so we connect that cancer data back into the splitting of the data, and we rerun it. And what you're going to find, actually, there is minute difference. Yeah. Okay. So, questions?
Where did you get the create our model? Is that pulled in from the
This is pre-built, this is pre-built in the R component.
Sorry, I
So
missed that.
only two things, a trained model, and a script. So you can run your own script.
I mean, physically, how do you really?
Oh, drag and drop. I'll show you where. Our language modules. Okay, this is the one that we use to train and okay, and this is the one that I was messing around with to try and run some scripts on R. And like I said, I ran into not all are available, and we needed to load the proper libraries and all of that. So. We won't be able to demonstrate much here, okay? But I think we covered quite a bit of R, right? How many people are interested in learning R? Wow, nice, nice. Will you come on Saturday and see us actually demonstrate and talk about the boot camp that we have on the 6th of May? We're gonna have it in same place here, but next room at the Speakeasy. Okay. Now, Frank at AnovaAnalytics.com. Send me an email. I'll make sure I'll send you a packet of information and the details about next Saturday. This Saturday, sorry. Yeah. So in 3 days. Fantastic. You're gonna show?
Yeah, I can show some.
Yeah. So now, if you want to